Good evening. It's a true pleasure for me to be here this evening at the beginning of a course which looks amazing to me. Actually, I looked at the program and you're in for a treat. Absolutely. So I wish I could stay actually and learn a lot. I also want to emphasize what Kun has said. Actually, you should use this as a way to build a network. Your network that basically is going to be with you for the rest of your life. So it's very important. Those type of events help my career a lot. So I just want to make sure you do the same thing. So I'm going to give you this evening some perspective on what I call, or what a number of people call the compute continuum. I might have a slightly different twist of it, but my whole life has always been about energy. Low power, energy reduction, and so on and so forth. So I'm going to primarily stress the energy perspective. But first, let us get some, it's kind of interesting. I think this antenna is very directional. You have to be here to flip your slides. Let me go back a little bit and talk a little bit about the evolution of the compute platform. When I started my career, late 70s, 80s, computers were isolated entities. They basically were emerging, but they were not connected. There were big things in a room, and they all basically operated individually. Fortunately, some networking started to appear. It was clumsy. You had to have big coax cables to connect your computers, but ultimately we could make computers to work together. And slowly but surely, mobile devices started to emerge as well in the late 1980s. Now go 10 years forward, and we go to the 1990s, 2000s, and a new thing emerged. Obviously, networking became ubiquitous. We could connect computers together all over the place, and at the same time, mobiles start to appear. Digital, wireless networks start to become into the game, and it changed our compute platform, because now we had computers connected at the core, which were compute and data servers, and then we had a circle of mobile devices around it that provided us access to that compute capability. So the interesting part is that we had millions of compute elements at the core, but with the mobile part, it basically we got a gigantic growth, and we had billions of devices ultimately connected to that network. All right, another 10 years forward, and the next thing happened. Wireless sensor network. Suddenly we had wireless sensors that were spread around the world that helped us to basically connect that compute, that cyberspace, to the real physical world, getting information in and out. I tended to call this the swarm of computing devices or edge devices. You can call it also cyber physical system, sensor network, IoT, you name it. But again, it changed your compute platform. And now, instead of having billions of devices, we start to think about trillions of connected devices around the space. So that's where we were about 10 years ago. Where are we going now? Well, it's the next layer. It's what I call the living network of everything and everyone. By now having sensors and actuators connecting that physical world to the cyber world, we are creating a world where everything is connected, where we have autonomous devices, we have healthcare devices, we have robotics, we have autonomous vehicles kind of working together. So it's a living network of everything and everyone. Okay, so that leads us to the next thing. If you look at it, we tend to look at it from our angle we're used to. If you're basically a high-performance computing person, you look at the computing at the center. If you're a sensor person, you look at the sensors on the side. But if you take a step back, what you see what we created is a gigantic computing platform that spans the Earth. Everything on Earth is now being connected, and computing is everywhere. That's what we call the compute continuum. It's intelligence everywhere. And it connects basically this virtual world with the natural world through edge devices and so on and so forth. It's an interconnected ecosystem that allows complex applications to execute it from IoT edge device to the HPC cloud. Ultimately, you don't really know where your application is running. It could actually use all layers of the whole system. Okay? And it also offers a new opportunity in the sense that it moves computing to where the relevant data is sitting and where resources are available at a minimum cost. So computing is not something that's fixed in space anymore, but actually can move with the needs of the environment, the needs from computation, and so on and so forth. So, very exciting, very complete picture, and obviously this is happening today. There's a number of those platforms that really cover this basis. And obviously, yeah, before I go there, intelligence is everywhere. We are now in the age of intelligent devices, and it's going to be at the core, where we might have general intelligence, things that tackle hard problems and help you to collect lots of data and make sense of that. But at the same time, you see now devices that help us to assist as humans, agentic AI as we call it these days, but again, all those devices that help us to do our daily life, in parallel with autonomous cohabitants. Things that basically are walking around us and acting around us to basically help us out. And then finally, it also starts to encroach on who we are as humans. Basically helping first of all with human health and wellness, helping to correct problems we have as humans. But ultimately, it's clear that it's also going to lead to some form of human augmentation, making us capable to do things that would be otherwise very hard. So, AI is going to be part of this whole picture. That's no question about it. So another way of looking at it is what we're creating is what you may call a mirror world. We're actually taking our real physical world and we're running in parallel a gigantic simulation or a model that basically models what's happening in the real world. We have all those sensors in the physical world, getting the data, sending it to the cyber world where we have simulations, models, generators. But ultimately, those devices are not basically just doing data, they actually feed back. That's why basically it actually impacts what's happening in the real world as well. So they live together in parallel. The mirror world is kind of this representation of the real world in digital form, and there's a bidirectional bridge between the two. Now again, as I said, this sounds like kind of crazy, but it's already happening. There's a number of examples that are basically of what a mirror world could look like. Typically, they tend to be focusing on one particular space. And there's a number of examples of space that fall under this class, like for instance, mobility is one. Yeah, for instance, when I drive one of those EVs these days, I have all those sensors around me and I learn around the world around me by having the local information, but that's not sufficient. What you're doing is basically also using global information that's available that you don't see from your car yourself, but basically tells you where traffic jams may be happening, how things are moving, what you may predict of what's going to happen with traffic coming down the line as well. And this is true for mobility, but it's also true for environment and agriculture. It's really starting to happen that we see virtual worlds in the agricultural space, weather, climate, energy networks, even system design and operation are all basically now being driven by this mirror world, and automation and manufacturing. So a number of those stovepipes, and unfortunately, they tend to be disconnected from each other. Actually, if you could connect them together, you would get a much richer type of environment and even more information available to you. So, where does it leave us humans? And I think humans are an essential part of the mirror world. Again, today we're starting to wear sensors on us. We have our cell phone with us continuously, keeping a lot of data. I wear watches, I wear rings, all kinds of things to observe how my body is behaving. So humans are going to be an essential part of what such a mirror world or a compute continuum could look like by having indeed sensing, networking, communication, and actuation devices that allow us to connect us as humans into this particular space. And what it allows us to do is a variety of things, like obviously a digital twin of the human body that basically warns us if something is going to go wrong. But it also can help us to live in a world which is increasingly more complicated. Think about elderly people basically working in space where things can adapt to their needs on demand. Or ultimately, I think, in the way when we start connecting the human brain into the system to brain-machine interfaces. Again, this sounds like science fiction, but it's happening faster than you think. All right, so I think a very exciting background space here. There's a lot of interesting things happening, and it's moving very rapidly. The question is what it takes to make it happen. What are the needs looking forward if we really want to get such an environment to create? And I'll just get you some numbers, some predictions. So number of sensors. So sensory information is very important to the system. Well, the prediction is that the number of sensors being deployed, or the amount of data gathered by sensors, is going to grow exponentially. By the year 2032, we're going to talk about 1 brontobyte per year being collected. Now, you might never have heard about the brontobyte. It's about 10 to the 28 bytes. Now, think about us as a human. I walk around a single day. Through my senses, I collect about 70 gigabytes per day. That's kind of the numbers by looking at your eyes and your skin and all those kind of things collect about. So you think about the whole population of Earth, you multiply with that, and you see that this curve is even rising faster. So the amount of information we're going to get is humongous, and it's keeping on growing. That's a challenge. So now information is a good thing, but you have to bring it somewhere where it's useful. So you have to have networking. You have to have networking capabilities with them. Again, if you look at the predictions, we see that wireless capacity, the amount of bits I can transmit wirelessly, is also increasing exponentially. So that's good. There's one unfortunate thing though. Sensor data, as I said, basically your brontobyte is about 3 to 10 to the 19 bits per second. Now the communication capacity by 2030 is going to be 10 to the 16. So we have a gap of in fact 3 orders of magnitude approximately. So what this says is, transmitting all those raw data doesn't make any sense. We're going to have to put computation in the sensors and limit the amount of data we're transmitting. Okay? So wireless capacity, we're going to need to store all that information, which is also going up exponentially. So the amount of storage is going to grow substantially. We need smart storage. Store information, not data. That's quite essential. Otherwise, we are going to overcome even what this capability will give us. And then finally, computational load. The computational load to basically run such a mirror world, run this compute continuum, is going to increase exponentially as well. So here's a quote from Intel. If you just take the metaverse, which is one example of a mirror world, it takes about 10,000-fold increase in compute capabilities. That's an Intel statement, and it's probably going to be in the right direction. But my perspective is it's going to be even worse. What we're trying to do is build a model of the Earth, running parallel with the Earth itself. And if you think about that, how much complexity you have in that, that's mind-boggling. So actually, the Earth's complexity is non-computable, is one statement. It's hard to figure out how complex the Earth really is, and it's basically leading to limits of scaling, laws, and so on. So the Earth is a complex system because it instantiates at a planetary scale. Its life is important, is a part of that, and something we don't have a hold of. So, huge challenges, right? Exponentials and everything, and we need to have a compute platform that basically allows this type of thing to happen. So, lots of challenges in this live world, and I can mention a whole bunch of them, and some of them are going to be covered in these courses here. It's about scale and integration. How do you scale up systems like that so that they're robust, so that they're transparent, that they're secure, that they're private, that liability issues, ethics, all those type of things are humongous issues to address. And it's going to keep you guys busy for the next decade for sure. But as I said, my life has always been about energy, so I'm going to look at the energetic perspective of basically making this type of things happening. Okay, let's look at energetics, and again, we have to look at the various aspects. Even though I consider this one compute continuum, depending on where you do the computation, you will see different emphasis, right? If I basically look at the cyberspace, the cloud, there we talk about trying to do computation as fast as possible, right? That's the key goal. And you want to get very fast data rates to make that happen. So terabits per second data rate, millions of serialized nodes, and again, more sticking to traditional architecture like Von Neumann. If on the other hand you talk to the natural world, there's a very different perspective. You want to be just fast enough to interact with the world, to make sure that the right data, it's as fast as needed. Instead of gigabits per second, we talk about kilobits of data rate. You talk about nanowatts of power, where on the other side we talk about mega or gigawatts of power. So very different, and obviously the solutions are going to be different depending on where you are in this continuum. So let's look a little bit at some of the computational requirements that basically are emerging and how are we going to tackle it. So obviously we see the challenges. What are the solutions to the problems? And again, here's one of the big challenges. This is a slide from Lisa Su, who is the CEO of AMD at ISSC about a couple of years ago, where she showed how the compute performance of the high-performance computing space is actually going up exponentially. It actually doubles the performance every 1.2 years approximately, which is amazing, right? Double performance, 1.2 years, to all levels of optimization, better technology, architecture, system, everything coming together, giving that performance increase. So it's pretty cool. But if you look at the other side of the story, if you look at the energy efficiency of that computing, it's also going up exponentially, but there's a problem. It doubles the efficiency only every 2.2 years, so there's a gap. And we basically are creating a challenge here. To just get that gap even more clear, if you think about performance, 100x over every 9 years. From an energy perspective, 100x every 14 years. So filling in that gap is going to require us to come up with new solutions. We're going to have to come up with bold ideas to basically get around that. Now, what this leads to, and again, you've heard this now a million times already, the fact that we basically have this inequality where we're pushing performance, but the energy efficiency doesn't follow. You run into gigantic problems from an energetic perspective. Those data centers now basically rising at an exponential rate. By year 2030, it's about 11% of our overall power is going to go into this data center type things. Now that's known, and we have to come up with a solution for that. But it's not the only one. We always think about, oh, this is only data center. But think about all those IoT devices, all those sensors. Again, we have billions of those things deployed, hundreds of billions actually. So if you take the very simple math, so okay, on average such a node might use about 500 milliwatt approximately. And you do the cycle of at 50%. If you have 80 billion devices, you're going to consume 170 terawatt hour, which means 300 million solar panels or 350 gigaliter of lithium-ion battery. So it's not only the cloud that's going to push the power requirements, it's also at the edges that we're seeing the multiplication of devices is going to cause problems. So we need new solutions. And too bad, to basically make all those things harder, is that our traditional button, or traditional twisting, which is technology scaling, isn't helping that much anymore. We see that actually making transistors smaller and smaller, we still can do it, and I'll show you in a minute, is not buying you a lot of performance, it's not buying that much energy efficiency. It still gets you more transistors per unit area, which is good. But from an energetic perspective, it doesn't buy you that much anymore, which I call the end of Dennard scaling. So here's kind of my projection of where we may, or where we are going to help address some of those problems. Okay, as I said today, we're doing, from a technology perspective, density scaling is still going on, and is going to go on for the next 10 years for sure. So we're going to make density going better. But it's going to limit, and today we're moving to other approaches like heterogeneous packaging, 3D integration, and I'll talk about new primitives in a minute. And that's connected to a number of improvements in the architectural space, such as parallelism, customization, use of locality and sparsity, and ultimately to adaptivity and intelligence. So I'm going to walk you through some of those steps and see how things are evolving today and in the next decade or so. So let's start with density scaling. This is a slide that some of you may have seen. It's a traditional IMEC slide showing the roadmap of how transistors are going to scale over the next 10, 15 years. So today we're in the FinFET age, very popular, very effective technology, and we're moving to what's called the nanosheet area, where we actually have now still fins, but they're kind of wrapped around the channel, getting better performance. Okay, so that's happening. The next thing that will emerge is what's called CFET, where you put the PMOS and NMOS on top of each other. So once again, getting more density from an overall transistors or gates per unit area perspective. After that, we're talking about 2040, 2035 approximately. Those numbers, every time I see those AMIC slides, the numbers shift by a couple of years and towards the future. 2D FETs and things like that, but again, a bunch of question marks at that point in time. And you can see the number of metal layers going up and all this type of thing. So what does it do to you? Well, it buys you something, going, let's say, from the N2 node to the, from the N3 node to the N2 node, which is happening right now. It bought us about 30% better density and about 30% less energy per basically gate or per. If you go to the next step, we'll get some less, still some improvement in energy, but the density won't scale that much. But ultimately, if I look at this whole scale, I see about 2 to 3 factor energy reduction by 2033. Now think about that, that's not bad, but it's a very expensive solution to basically help to tackle the problem. And the cost of this per transistor is going to go up. So it's going to help us some, but it's going to be expensive and not clear if it's going to help you all the spaces you need, definitely not towards the edge of the compute platform. So question is, what's next? Ultimately, we are pushing against the 2D perspective, right? Basically, putting things closer and closer. We've done very smart things, but ultimately going to get stuck. We're going to have to be forced to move out that two-dimensional scaling perspective. Are we completely out of gas yet? No, because we're smart. So people keep on coming up with new type of transistors. 2D transistors are now something that people are looking in for an advanced thing. But other materials, what's happening in the material science space is incredible. So for instance, ferroelectric gates suddenly might allow us to basically run at very low voltages, 300 millivolt, and get about 5 to 10 energy reduction at minimum speed degradation. So that's very attractive. It's very speculative. We cannot build those things yet at scale, but these are the type of things we have to keep in the back of our mind if we move forward. But ultimately, we're going to get stuck, right? Atoms are only that small. You cannot get smaller than that, so we're going to have to be smarter than that. So the next thing basically comes down is about a very important thing in computing that everybody in high performance computing work is locality is very important. If your data and your compute are intermingled with each other, as close as possible better, we're going to save quite a bit of energy. We basically get rid of some of the overhead. And again, there's some sessions going on in this course about, for instance, in-memory computing. In-memory computing using DRAM or in neuroelectric type systems and so on and so forth, where memory and data basically gets intertwined with each other. And nowadays there's also a lot of movement in the optical space that allows to get data energy efficiently over a certain distance between compute nodes. So there's a number of ways for us to create locality. It doesn't have to be physical, it could also be energetically. Now, having that, we are basically going away from the 2D perspective. Basically moving from 2D to other ways of getting some three-dimensional perspective is something that's very attractive and obviously is happening. And the first thing is happening is chiplets. They're all the realm of today. Everywhere you go, people are talking about chiplets, stacking transistor or chips on top of each other using some advanced interconnect or packaging capability. But again, this allows us to customize, use the right technology for the right thing, and put it together in an integrated format. It also basically helps us to get 3D kind of capabilities. Now, if you want to push it to the extreme, what I really would like to do is build real 3D devices. Again, why do we get stuck on our 2D? Why not basically stack transistors on top of each other? Again, this is an animation from IMEC, which shows that I could make a number of wafers, basically optimized for a certain thing, like logical transistors, driver transistors, memory, multiple styles of memory, input-output capabilities, even power delivery. You can pick all those wafers and then using advanced stacking and packaging technology, we can put all those layers on top of each other very densely, building true 3D capabilities. This is something that we call CMOS 2.0, the next generation of CMOS integration. Now, one way to think about this is say, okay, what is this? Is business as usual, we just have more three-dimensional, but I think it's the wrong thing. Once I have the capability of being memory and logic and all the stuff things so close to each other, sense, I need to rethink the way we do design. Rethink how we basically select our primitive components. Are they still going to be traditional gates? Or basically doing placement, routing, synthesis, timing, verification, architecture. Everything changes if you start thinking that way. So thinking out of the box, if you have that kind of capability, is going to be very important. Now, here's an example of some of those out-of-the-box thinking. I said, well, if I have this 3D capability, why can I not use that to build, let's say, neurons? Neurons are very three-dimensional things where you have the cells and you have synapses that connect to all the places over. Can I not use that technology to mimic something like that? Using, for instance, CMOS neurons. And this is an example of a neuromorphic chip where you indeed use all those layers to put neurons in a very dense connectivity. Now that feeds me into the next part of the presentation, thinking about actually getting inspiration from other spaces. We've basically been thinking about logic always as digital gates, Boolean logic, all these kind of things. But it's time to think about, are there other primitives? And obviously that's what we're doing today, right? The whole neural nets type of movement obviously has basically been driven by basically inspiration from the biological space. Now here's an inspiration from the biological space when you think about locality. What makes the brain so different? Well, there's a number of things that make it different, but here's one. If you look at a typical digital design, a double gate, the average fan-in, the number of inputs to a gate is 4. That's the optimum number. Now, if I look at the brain, the average number of inputs to a single neuron is 1,000. Now what does that do to you? Well, it allows me to build very dense networks with few layers. Actually, there's an interesting number that the network diameter, which is the average hops between two elements of the network, in the internet is about 10 to 15 approximately. It's an estimation. But to go from one node in the internet to another one, you need about 15 hops. In the brain, you need about 3. Every neuron is about 3 hops away from every other neuron. Why? Because of those very large fan-in capability. So if you change that picture, we suddenly are rethinking how we could build computer architectures. So that brings me exactly to what I said. Maybe it is time to think about revisiting our computational primitives. Again, we've been using analog circuitry, digital circuitry for a long period of time, and it served us well. It was an amazing abstraction that allows us to build extremely complex things that work. But maybe at some point in time we have to think broader. Maybe get some inspiration from biology and physics. Okay, so why biology? Well, as again, I pointed out to the human brain already, 80 billion neurons, which is 100 trillion synapses. So this is about the complexity of the most advanced ChatGPT model as we're talking about today, right? In terms of number of synapses approximately. It does a lot of computation at an average power of 20 watts. Now, interestingly enough, you would think that a brain is very efficient in its primitive use. Actually, the neuron, when you fire up a neuron, actually it turns out to be not that efficient. It takes about 250 picojoules to fire a neuron. So why is the brain so efficient? Well, it tries to minimize the number of firings. It's very sparse. It tries to, so at any point in time, only 0.2% of the neurons are active at any given time. So sparsity, only turning on what you need to turn on, is really important. The other interesting part is your brain is cheap. So from an energetic perspective, I think about the way you feed in the energy, you get your food. So I make an estimate here, depending on where you are in the world, and maybe we take about $10 of food per day. So that's the cost of energy per day of running that amazing computer, right? Very efficient. So, but the key property is it's slow, it's sparse, and it's local. Locality is very important. Now, obviously this has led to our inspiration of building neural nets, and again I show you these things, it's amazing. ChatGPT 4, basically the NVIDIA GPU, 1 trillion parameters, 2 million neurons approximately. It's not to the 80 billion neurons yet, but we're going that way. Now let's look at the cost of this. Again, this is where one of the challenges are. So the energy per neuron activation, if I look at an NVIDIA processor and I compute the energy I take to do one neural simulation, it takes about 250 picojoule, 200, 300 picojoule, which is about the same as the biological equivalent. They're about the same number. But what they're different in is activity and sparsity. You now do the analysis about forward passes, training and things like that. The full training run is about 100 megawatt hour or 0.4 terajoule to run basically one of those training runs. At the energy cost of about 0.1 kilowatt hour, which is cheap, it's about $10 million. Remember the $10 for our brain? $10 million right here. Right. Now, obviously, this is brute force. You can do better. And yes, people have come up with optimizing those things, like for instance what DeepSeek has done is making sure that you do a lot of manual labor, you can optimize the network, and indeed you can get about a factor of savings of about a factor 10 approximately by basically optimizing the network. But you're still stuck at that large number. So we need to think about, do you always need those huge networks? Do you always need this type of thing? Like for instance, already here you see that you have a mixture of experts in the DeepSeek type systems. Now, if we now change the primitives, if we say, well, I'm not going to basically compute neural networks using multiply accumulators of digital gates, but I basically built a real neuron as the basic element, suddenly you can do a lot better than that. Energetically. Neuromorphic is an example of this. There's a number of examples out there. If you take a GPU, 200 picojoule per neuron, as I mentioned, if I take a neuromorphic approach, I probably get to a femtojoule to about a picojoule. So orders of magnitude improvement by changing the primitive operator of the structure. And you also have to realize that you don't always need that very complex network. For instance, an example that basically been studied quite a bit in the biological space is what's called C. elegans. It's a worm that basically behaves quite nicely. It can move, it smells, it can find food, and things like that. And it uses 300 neurons. That's it. And the network is pretty well known, so with 300 neurons, it does a lot of complicated behavior. You don't need billions of devices. So some people start to realize that, and there's other ways of basically building your neural nets that could be more effective. Like for instance, the liquid AI uses a more complex model of the neuron itself. But you can start building neurons using, for instance, magnetic devices or other things that basically might help to improve the efficiency substantially. Okay? So the other part, as I said, that's the biological part, but it's also worth looking at physics as a way of computation. So one of my colleagues, Eli Jablonovich, who's one of my colleagues at Berkeley, gave a presentation at ISC this year where he said that all optimization approaches are versions of physically based minimum entropy generation. You think about automation like simulate annealing and things like that, it's ultimately what you try to do is minimize the energy of a complex network. And we can do this differently. We can actually do optimization using new elements, like for instance oscillators, icing machines, which basically use noise. Or we can actually have silicon photonic optimizers that basically help us to basically start with an initial condition, and using random moves, you basically move to an optimal point, solving very complex optimization problems. Or we can even mix it with the biology part. So physics-informed machine learning is an interesting space as well, where the back propagation is now replaced by actually physical equation, like Navier-Stokes loss equation. You start putting physics into your neural model. Again, helps us to get better efficiency for very complex problems. Now, if you think about the most extreme of the physically inspired computing, is something, there's another track in this course here at now, is quantum computing. Quantum computing basically we're going to change the primitive element, we're going to use it, we're going to make it statistical. A statistical thing called a qubit, there's also something called p-bits and things like that. So a lot of movement here. Again, what it's going to do primarily is help us to solve complex optimization problems. That's really what quantum computing basically is primed for. And potentially, obviously, it can lead to much better energy efficiency, but you have to take the cooling into account. But from an accelerated perspective, again, it's a new inroad to computation, which is now basically purely based on physics. All right. So, this is I'm almost at the end of my prediction curve here. I have one thing left, is activity and system intelligence. Again, the key thing which I basically put up in the beginning when I talked about the compute continuum is compute the right thing at the right place at the right time and provide energy accordingly. You basically do computing where energy is available, or you make energy available when you need to do the computing. And again, there's you can think about a grand scale, but to me, again, inspiration from biology here can help to think of how this may happen. And again, I took some pictures here from one of the courses this week is going to be about compute continuum for scientific applications. Again, it's looking at how to program such a system basically effectively. Another thing which I like a lot is this paper which is called the Scalable Compute Continuum. And one of the statements here, to fully realize the compute continuum's potential, autonomous and proactive management is essential. It is not purely about programming, it's about management of the system and how and when computing is being performed. So it requires leveraging interdisciplinary methods from optimization theory, control theory, machine learning, and artificial intelligence. It's all coming together. And again, as I said, we could get some inspiration here by the biological space. If I look at the human body and how we operate, we have something which is called metabolism. It's the process that provides energy for growth, reproduction, and repair. So we basically get food in and we turn it to energy at the place it's needed and at the right time. We also have physiology, which explores how organs, tissues, and cells work together to maintain life and respond to changes in the environment. It's a collaborative environment of things together. And so it's part of our whole system. Metabolism, physiology is part of how our brain basically operates and performs functions, but not only the brain, but the rest of our body as well. The other part of the loop of the brain is obviously the one that basically helps us to observe the world and interact with the world. So with that, let me go and summarize. I think if we want to energize the compute continuum, we're going to have to, we're going to have a lot of challenges, and it's going to require changes. Obviously, the past is still not behind us. Density scaling, heterogeneous packaging, chiplets, all these things are going to help. But ultimately, we're going to need to rethink about things about locality, sparsity, new primitive of computation, and adaptivity. So, what it needs is innovation. So don't be scared. Be willing to basically take steps forward that maybe sound risky at a while, but ultimately can make a change in paradigm. And it requires inspiration. And inspiration can be found in the world around us. See how the world operates, and maybe you can learn from that to move forward. And with this, thank you for your attention.